Today we will be doing magnetic properties of matter. Now, thanks to chemistry, you people have heard of these two words, diamagnetic and paramagnetic. You know that all substances with no unpaired electrons are diamagnetic, and substances which have unpaired electrons are paramagnetic. So this is something which you know thanks to chemistry. Now the thing is that every electron is a charge in motion. And every moving charge has an associated magnetic field. Now it is found that if you have no unpaired electrons, that means all the electrons are paired, then it is found that the magnetism cancels out in pairs. So if there are no unpaired electrons, which means if all the electrons are paired with each other, then the magnetism cancels out in pairs. Now if there are unpaired electrons, then there is a net magnetism. Now imagine that there is a substance, and this particular substance has unpaired electrons. So due to unpaired electrons, each atom has a net magnetism. So we can substitute an atom by a dipole. So you will notice that I have drawn a diagram over here. In this diagram you can see that I have shown some magnetic dipoles. All these are magnetic dipoles, and each dipole is basically replacing an atom, because that atom has unpaired electrons. So you are replacing the atom with a dipole. But look at these dipoles very carefully. You will see that these dipoles are aligned in a random fashion. They don't have any orderly alignment. The alignment is completely disorderly. Now suppose you apply a magnetic field. Suppose you apply a magnetic field, then what will happen? All these dipoles, they will start aligning themselves according to the field. And if you take a certain volume, suppose you take a certain volume V, then the net magnetic moment in that volume is denoted by capital I, that is called intensity of magnetization. So once again, you have a substance which is paramagnetic, and you have the randomly aligned dipoles. All of them are randomly aligned. When you applied a magnetic field, then the alignment became perfect, or rather the alignment became orderly due to this field. And at that point of time, the magnetic moment in any volume, or rather the magnetic moment per unit volume, is known as intensity of magnetization. So if capital I is very high, that means this substance is strongly magnetic. If capital I is low, that means the substance is weakly magnetic. To explain this further, let us say you have a substance whose initial dipole alignment is like this, and after applying a field, the dipole alignment becomes like this. So you can see that the dipole alignment was pretty strong initially, and after applying an external field it has become further strengthened. Such a substance is called ferromagnetic. So this is what I was telling you about the capital I intensity of magnetization, that it will be very high for ferro, and it will be comparatively less for para. So an external field really intensifies the magnetism inside a ferromagnetic substance much more than for a paramagnetic substance. On the other hand, there is a third category, that is known as diamagnetic substance. Diamagnetic substances, as you know, they don't have any unpaired electrons, all the electrons are paired. So there are no dipoles, but when you apply a field from outside, then dipoles are induced opposite to the field. So I have applied a field externally, and now the dipoles are induced opposite to the external field. So this is what happens in case of diamagnetic substances. Suppose there is a conductor carrying a current I, and there is a point P at a distance d from the conductor. So assuming that this entire assembly is in vacuum, the magnetic field at the point P, assuming this is an infinitely long conductor, the magnetic field at the point P will be equal to mu naught I by 2 pi d. So this is the field at the point P. Now the thing is, if you remove mu naught, then this expression I by 2 pi d, this is known as magnetic intensity. At P. So what exactly does magnetic intensity represent? Magnetic intensity represents the magnetism in vacuum. So there is no substance or material at the point P, it is pure vacuum. At that point of time, the magnetism at the point P, that is known as magnetic intensity. Now, since magnetic intensity has the same unit as magnetic field, so that is why it is a vector. And another thing is that now suppose you put a substance at the point P, suppose you put a substance, then naturally the dipoles inside the substance will start aligning according to the field at the point P. So that means there will be intensity of magnetization. So magnetic intensity is there because there is a source of magnetism, a current carrying wire. So that is why magnetic intensity is there at the point P. Capital I is there because you have now put a magnetic substance, and the resultant of these two times mu naught is called the magnetic field at the point P. So up to this point in the entire magnetism discussion, whenever we wanted to refer to magnetic field, we always used B, but now we will classify it like this. If it is vacuum, then it is H. If there is a substance, then for that substance the intensity of magnetization is I, and the resultant of these two is the magnetic field. Suppose there is a material for which H is the magnetic intensity, I is the intensity of magnetization, and there is a constant of proportionality which is pronounced as chi. This is a Greek alphabet, it is pronounced as chi. So capital I is chi into capital H. So chi is called the susceptibility of the material. Okay, chi is known as the susceptibility of the material. If the susceptibility is very high, that means capital I is high, so the substance is strongly magnetic. If the susceptibility is very low, that means it's weakly magnetic. Now just remember one thing, for para susceptibility is greater than 1. For para susceptibility is greater than 0. For dia susceptibility is less than 0. And for ferro susceptibility is much greater than 0. It is in the region of thousands. So susceptibility gives us a mathematical expression to understand the magnetism of a substance. There is another measure of magnetism of a substance, that is called permeability. You know that B is equal to mu naught into I plus H so that is coming mu naught into H plus chi into H. So mu naught into H into 1 plus chi. Now this mu naught into H into 1 plus chi is written as mu into H. So mu is called the permeability of that particular material. So basically you can see that mu is mu naught into 1 plus chi. This is the expression for mu. So if you divide both sides by mu naught, you will get mu by mu naught is 1 plus chi, and this is known as relative permeability. So relative permeability mu by mu naught is equal to 1 plus chi. If you are talking about a paramagnetic substance, relative permeability is greater than 1. If you are talking about a diamagnetic substance, relative permeability is less than 1. If you are talking about a ferromagnetic substance, relative permeability is in the measure of thousands, so it's much greater than 1. Now we come to a very important part of paramagnetism, Curie's law. Curie's law investigates the temperature dependence of paramagnetism. It says that the susceptibility of a paramagnetic substance is inversely proportional to the Kelvin temperature. So the concept is that if you increase the temperature of a paramagnetic substance, the dipoles will get more random and therefore the susceptibility will reduce. And this constant of proportionality is known as Curie constant. So C is known as Curie constant. Now suppose there is a ferromagnetic substance. Now we have seen that the magnetism is inversely proportional to the temperature. So suppose if it is a ferromagnetic substance, then on heating, after some time, the dipoles become random and it becomes paramagnetic. So the temperature at which it becomes paramagnetic is called Curie point. So after crossing the Curie point temperature, the substance changes from ferromagnetic to paramagnetic, and after that the susceptibility is inversely proportional to the excess temperature over the Curie point. So for a ferromagnetic substance, susceptibility is inversely proportional to T minus the Curie point. Okay, now we come to the next part of this chapter, that is hysteresis. Suppose we'll begin by discussing that intensity of magnetization is B by mu naught minus H. So let's say you're talking about a solenoid. So all of you know that in a solenoid the core is made of soft iron. So for a solenoid, if there is no core at all, without any core, it's vacuum, then H should be equal to Ni, because you know that the magnetic field associated with a solenoid is mu naught Ni. So if it is vacuum, H should be Ni. So this is the formula for a solenoid. So capital I, that is magnetization intensity, is B by mu naught minus Ni. Now let us say right in the beginning the current is off. Now the current is switched on and the current gradually increases. So if the current gradually increases, what happens is that the dipoles become better and better aligned. However, the dipole alignment has a maximum limit. So there will be a point in the graph where the dipole alignment will achieve saturation. So let's say that there will be a point such as A. So at the point A, the dipole alignment will achieve saturation. Now, after the dipole alignment becomes saturated, if you suppose reduce the temperature, you will see that the graph will not retrace its path. So at point A, the dipole alignment is saturated, and now you have decided to reduce the temperature. You will see that the graph will follow the path AC. Now OC is called the retentivity of the material. So what does it tell us? This is a y-axis is capital I, x-axis is capital H. So retentivity basically tells us that even after you remove the current, there is a net magnetism. So OC is called the retentivity of the material. Now what you do? You reverse the current direction. Reverse the current direction. You have already decreased the current to 0. The current has already become 0 at the point C. Now you reverse the current direction, and finally when the dipoles become totally random, you reach the point D of the graph, So OD is called coercive force. That means that by some coercion or by some external means, the dipoles were forced to become totally random. That is why OD is called coercive force. Now what you do is that you continue the graph and you keep increasing the reverse current till the dipoles again achieve saturation. So that point is E. So at the point E, again the dipoles achieve saturation. Then again you decrease the current to 0. So the graph will follow the path EF. And from F onwards, again you increase the current in the original direction, and you will see that the graph will follow the path FGA. So this entire loop which we have drawn, that is A, C, D, E, F, G, A, this loop is called hysteresis loop. So this loop is called hysteresis loop. Now, if you are studying a substance like steel, then the hysteresis loop area is very large. So it is found that the area is proportional to thermal energy loss, or you can say thermal energy dissipated. See, when you look at the hysteresis loop, you see that there is a forcible disalignment of dipoles occurring during the hysteresis cycle. So, if you have a strongly magnetic substance like steel, then the retentivity will be high, coercive force will be high. So, the forcible randomization of dipoles will involve thermal energy loss. So the area is proportional to thermal energy dissipated. So for steel, if the loop looks like this, let's say this is the graph for steel, then this will be the graph for soft iron. So in case of soft iron, the thermal energy loss will be much less, because you can see that the retentivity and coercive force are much less. So where do we use steel? We use steel whenever we want to make permanent magnets. We use steel whenever we want to make permanent magnets, because you know that once it is magnetized, the retentivity is very high, so the magnetism will not be easily destroyed. Where do we use soft iron? We use soft iron mainly to make electromagnets. And for making soft iron cores, so soft iron cores can be transformer, moving coil galvanometer, so electromagnets are used to make cores for transformer, for moving coil galvanometer, etc. So these are places where the magnetism is not retained to a large extent, and once you remove the current source, the magnetism is completely reversed. So that brings us to an end of hysteresis loop, and it also ends this particular session of magnetic properties of matter.